Welcome back to the Automation Podcast, the world's #1 industrial automation product and technology show. Thanks to you, our audience of highly skilled automation professionals. Thank you for being a member of our audience, and thank you for tuning back in this week. Now, for those new to the show, my name is Shawn Tierney of Insights in Automation, and each week I invite a new vendor to come on the show to tell us about their products and technologies. And during their presentation, I play the role of the audience, asking questions that I think you, the audience, have, and some questions I have as well. And given that a quarter of our audience doesn't watch but listens to the show, I also try to call attention to any visual details that I think you listeners may be interested in. And so, with that, I want to welcome first time on the show, Ashley from Endress+Hauser. And Ashley, before we jump into your content, can you just take a moment to introduce yourself to our audience?
Absolutely. Thanks for the introduction, Shawn. So I'm Ashley David. I am a product marketing manager for level and pressure products at Endress+Hauser, USA. So I focus on providing strategic vision, marketing direction, and helping out with the technical side of our products. I've been with Endress+Hauser for 8 years now.
Wow, that's great. And we were talking in the pre-show that you have a background actually with some hands-on and supporting it, and now you're marketing it. So we kind of had similar backgrounds where we were both like doing the hands-on, but also doing the marketing. So with that said, let's jump into what are we talking about today, and why is it important?
Absolutely. Having the background and hands-on, starting in our technical support and service group, radars are something that I have had a lot of experience with, both troubleshooting and speccing. And one of the big things that has been a hot topic in the industry is 80 gigahertz. And it seems like everywhere you turn and talk to somebody who works with radar, who is getting into radar, they're like, oh, do you have 80 gigahertz? And we do have 80 gigahertz. I think most manufacturers are going to offer 80 gigahertz now. However, while 80 gigahertz works for 80% of radar applications, that's still 20% of the industry. And 20% is a pretty large chunk where it wouldn't work. So I really wanted to talk about, where it does work, what its benefits are, and where you should look at a different frequency or even a different technology. So in addition to 80 gigahertz, the common frequency bands of free space radar, and I say free space because guided wave is its own beast, are your low frequencies, which are going to be your 6 to 11 gigahertz, your middle frequencies, 24 to 29. So you'll see a lot of people refer to them as your 26 gigahertz, and then your high frequency. So that's where our 80 gigahertz is going to sit. So characteristics and benefits of the new 80 gigahertz frequency, it operates at a much higher energy, right? So it has a much higher propagation speed. And the frequency and therefore the wavelength are decisive for several properties of radar. So when you think of antenna size, dimension of the process connections, et cetera. So we can have a higher frequency and operate with a much more narrow beam angle for longer distances if we're using something that has more energy.
Now I'm going to ask a question because I don't know much about this. Is
Sure.
the fact that it's 4 millimeters versus the other types, does that give us a better resolution? Like if you look at the 6 gigahertz, it's 50
hmm
millimeter, right? Do we
hmm
get better resolution the higher the gigahertz?
You can, and that can sometimes be a hindrance.
Oh, all right.
Sure can, yeah. So you do get better resolution, and that's where it also plays into the longer distances, right?
Hmm. Hmm.
So when we talk radar, one of the big questions we ask are, what's the dielectric of the product, right? How
Ah, yeah.
conductive is it? And depending on that dielectric, you may have a shorter or longer measurement range that you can achieve depending on the frequency of the radar you're operating at. So 80 gigahertz having much higher energy, we can see lower dielectrics at greater distances.
Okay. Okay.
hmm And it also gives us a tighter beam angle. So here's just a quick comparison of the different beam angles. Obviously, 6 gigahertz, your lower frequency is going to have a much wider beam angle. Or 80 gigahertz, we can get down to 3 degrees. So just a quick comparison there for segmentation. Beam width and beam angle are really important if you're trying to get around obstructions in your vessel.
Hmm.
So if you have a tank that has baffles or heat coils or agitation, An 80 gigahertz radar may be attractive because you can use that narrow beam angle to not have those obstructions in the way. Now, mapping or suppressing false echoes is something that we can do with radar, but if you can get the obstruction out of the beam entirely and you don't have to worry about it as much, then it's not a problem to begin with. However, every frequency has a purpose. So again, 80% of applications can use 80 gigahertz. The narrow beam can avoid obstacles. However, because it is such a high frequency, it's going to be more sensitive if you get condensation on your antenna. It's a very dusty process, right? If you have an extremely agitated process where there's lots of waves or foam or ripples, right? It's also not as suitable for stilling wells. So which is counterintuitive, I was actually talking about this today with a customer of mine. When you get that much of a high frequency radar in your stilling well, and you get all of those signals back, like all those concentrated signals, it can confuse the radar, especially depending on how narrow that stilling well can be. Your wider stilling wells aren't as bad, but if you get a really narrow stilling well, it can interfere with that signal because you're getting a lot of high resolution signals back. Where if you're looking at your 26 gigahertz radar, it has the wider beam angle, but it still performs better in the stilling well. It's not going to be as problematic when it comes to your dusty processes, your foamy processes, etc. However, when we're playing with 26 gigahertz, we do have to keep in mind things like signal absorption. A process that I think of with signal absorption is ammonia. So ammonia is a really, really tricky process to measure because the vapors actually get excited at 26 gigahertz. And so you get no signal at all. And it can permeate through Teflon in the higher frequencies. And so that's actually a product where, sure, you can use a lower frequency such as 6 gigahertz. However, I would move more towards a guided wave spectrum of radar, something with a graphite seal that you can't have the permeation of the ions through the elastomer seals like you would in a free space radar. So your lower frequency radars are fantastic against vapor buildup, foam, and they perform so well in highly agitated processes because by having that wider beam, you can see more of the process and kind of average it out. It is difficult to measure shorter ranges with 6 gigahertz though. And that goes into the different types of radars we have and how those measurements take place here. So when we're speccing a radar, some things that we're taking into account are your process media. So I know we talked dielectric constant earlier. However, ammonia has a pretty high dielectric. But if you're working with radar, oh shoot, this is ammonia. We maybe should look into different technology altogether. Buildup, how much buildup are you going to get on the face of this? If you have a process that's going to be splashing all over the face, if it's going to be sticking to the antenna, right, you might lose a lot of that with 80 gigahertz. How much dust or moisture is there going to be? Are we measuring large silos? Flower silos can sometimes be a little problematic. Sometimes we can just throw an air purge in there, and that's okay. Surface ripples, foam, antenna size, how tight of a beam angle do we need? And if you're deciding between 26 gigahertz versus 80 gigahertz, the tight beam angle might not matter as much. If you aren't measuring a long distance, your beam isn't going to get super wide at the bottom of 26. Whereas if you're measuring a longer distance, then it might be more important. So any kind of internal obstructions, how far off the side of the wall do we need to mount this? Do you have any heat coils on the side of the wall that forces us to mount to the center? A good rule of thumb with radar is 1/6 of the tank diameter away from the wall. Now, obviously, with smaller tanks, we have to, take into consideration, okay, we need to be more than 6 inches to a foot off the wall. But like if you have a vessel that's 6 feet across and you take 1/6 of that total diameter, that's an ideal spot to mount it. Mounting it in the center, actually, is something you don't want to do. You can cause false echoes by mounting something in the center. Oh, man, I wish I could draw the diagram for you. I'm always drawing this diagram in my classes that I teach with how the radar signal works with that. I'm a little bit of a radar nerd here, Shawn. So there are benefits to 80 gigahertz, which again, it's why people are talking so much about it right now, especially in solids. So a lot of solids that we work with are going to be lower dielectric. I'm thinking like grains and big silos. I'm not sure what types of facilities you were visiting as much, but when we're talking grains, we're typically talking low dielectric and really tall 100-foot silos. Although the best view is typically on the top of those 100-foot silos. So, I mean, you have to climb the ladder to get up there, but it's kind of nice once you're up there and you caught your breath. But so if you have a really tall silo and you can get a much longer measurement range with 80 gigahertz, that's going to be where we go first. But when we start looking at the grain size, right, you can limit your signal depending on, if you have too large of a grain size or if you have too small of a grain size with 80 gigahertz, in which case it could push us into looking at a 26 gigahertz or even a guided wave radar. So more benefits of it. It's great for avoiding obstacles. It gives you kind of you don't have to worry about antenna alignment during the installation. So with 26 gigahertz and 6 gigahertz, we're actually making sure we put a short side of the elliptical beam angle towards a wall. But with 80 gigahertz, you don't have to worry about that as much. However, it is more prone to absorption. So earlier we talked about ammonia and 26 gigahertz. Now, when it comes to 80 gigahertz, that's actually more common. So when we launched this into the market, we had an idea that 80 gigahertz could be more susceptible to the phenomenon of absorption. However, the longer we've put this in the industry, the more we have found that absorbs the signal. And so when you measure absorbing gases, it's better to use a guided wave radar or basically anything other than free space, right? So 80 gigahertz gets absorbed by acetone, by ethylene oxide, in addition to ammonia.
Now, when it gets
right?
absorbed, so you lose your signal, but is it also heating what's absorbing it?
It's not. So
Okay.
it's not a high enough frequency to cause, I'm not going to say it's 100% not, right? Like there is some physical phenomenon going on, but it has such a small impact on these large processes.
Okay.
But the ions, like the atoms get excited, and that's why you get no signal at all. Like there is just nothing the radar can even measure. And so when you throw an 80 gigahertz radar on top of a tank, and I have a customer or a field service guy calling like, hey, when I pull an envelope curve, which is a tool that we use to pull signals of radar devices, I don't see anything. I don't see any peak at all. I can see the launch, and the launch looks good, but I can't see anything. And the first question I'm going to ask is, well, how long has it been installed? Oh, well, it's brand new. So what's in the tank, right? And we actually maintain a document of chemicals that we've found over time have absorption. And, I'm going to run it through because I can't memorize. I don't know too many people who memorize every single chemical that absorbs 80 gigahertz radar. And, so we'll cross-reference it, and I can be like, oh, well, you're measuring acetone, so you're not going to get a signal off of that. You can't with the physical properties of it.
That's good to know. Yeah.
Yeah. And I actually have a picture here that one of my colleagues found comparing a 26 gigahertz radar to an 80 gigahertz radar. And you can see on the right side here, that's our FMR 52. So that's our 26 gigahertz radar versus the 62, which is an 80 gigahertz radar. The 62 is completely absorbed. You have a little bit of a launch, and then you get a bunch of noise. Whereas with the 52, you're getting a valid signal. And you can see right at the tail end of there where it's picking up on that blast peak and actually giving you that level measurement.
I see.
So that's what it actually looks like when it's fully absorbed. So envelope curves are super useful tools for anybody working in radar. It really lets you see what the instrument is seeing. Instruments can kind of be a canary in a coal mine, but people typically want to blame them first, even though they're just telling you something's wrong with the process, right? And so, depending on the process you have, you may not be able to pull the instrument off the top of the vessel, or you might not be able to climb 100 feet in the air.
Mm.
So, being able to connect in at a panel or at the device without having to break into the process or bring the process down allows us to kind of determine, is this a process problem or is this an instrument problem? In this case, it's kind of both, because it's an instrument problem because it's the wrong instrument. It's a
Mhm.
process problem because the signal's being absorbed. So that's something that we kind of handle a lot, process versus instrument. All right. So we have two different kinds of radar signals, and it's pulse versus FMCW, which is frequency modulated continuous wave. So your pulse radar are going to be your 6 and your 26 gigahertz, right? So it's a distance measurement based on time of flight between emitting and receiving the reflected radar signal. And the FMCW is the same, but it's more indirect. So you're like constantly sending the pulses. And you can kind of see the two different equations are slightly different with how they calculate that distance there. So, and I don't know if you want to dive into the propagation speed of microwaves, but just knowing that they are also two completely different types of radar pulses is what's key. And that's also what separates it and makes 80 gigahertz so much more effective at some of the longer spanned applications and lower dielectric applications too, is having the continuous wave.
Yeah, I think that in the formulas here, this is slide 13 for the audio audience. The formula is just so really interesting as you look at pulse radar. D equals C times T over divided by 2. Whereas I'm not going to go into the
Yeah, I
FMCW,
know.
but you're looking at it, you're like, wow, and you can see the min and max in there and a change,
hmm
and yeah, no, very interesting stuff. Thank you.
And that's because the frequency is modulated, right? So
Hmm.
earlier I showed a slide where it kind of showed that we were working in a span. So we're
Hmm.
not operating at 80 gigahertz every single time, right? Like it's a modulated frequency that's kind of set in a band. So when it's like F max minus F min, that's where we
Hmm.
start to get into what that means. I mean, I can nerd out about radar all day, but I think most listeners and viewers are, let's cut to the chase. Why is 80 gigahertz better or not, right?
Yeah, no, and I think pulse versus modulated really describes it well.
hmm
I just think it's very interesting just to look at, and I'm sure there's a reason why they modulate it. It seems like technology-wise, that's more difficult to do in your circuitry, right? But there must be
hmm
a lot of benefits to doing that as far as getting better accuracy. But I almost wonder, and then maybe this is an open question for you. I almost wonder, like, because it's 80 gigahertz, did they have to modulate it? Could they not pulse it? Was it
Correct.
not as effective as being pulsed? Is that correct?
It's not as effective if it's pulsed. It's just such a high frequency.
Hmm.
So you start getting into, basically having a frequency sweep
Hmm.
and having a band that you're working with. It allows you to kind of code the frequencies more. I'm trying to think of the best way to describe that. Um,
No, I mean that makes sense because you think
yeah.
a dumb pulse, it's like, well, it's just you're just pulsing it, right? That's very low
hmm
tech. And
hmm
so if you're doing a sweep there, going through a range of frequencies, a lot more electronics to process that, but I imagine you're getting a lot more information from that as well, right?
You are,
And
and you're taking measurements in a much quicker pace.
oh yeah, because it's a faster. Now let me ask you this though: can you actually tell or make a good guess of the material you're sensing from that?
So I can tell if we're like, I can pretty easily tell if we're dealing with a high dielectric or a low
Okay.
dielectric,
Yep.
right? And based on what a customer's telling me, like if I know what kind of process we're in, I can look at something and be like, oh, we're probably dealing with hydrocarbons.
Hmm. Hmm.
Or I can tell if it's a solid or a liquid. But I probably couldn't tell you what hydrocarbon I'm looking at.
Sure. Because
Or,
they're so
I
similar.
couldn't.
Yeah.
hmm so anything, if we get something that's similar in dielectric content and similar in like grain size, if we're talking
Hmm.
solids, I'm not going to be able to tell between those as much.
Yeah.
But if I have an oil water process and I'm dealing with a guided wave radar, I can look at the way the signals look and I can tell you flat out, you've got water in your oil or you don't.
Oh.
hmm So there are some things that we can, especially with the envelope curve tool I was talking about earlier.
Hmm.
And that's kind of a vendor neutral tool. A lot of vendors use envelope curves as a tool. They are so key and crucial to maintaining radars if you have the option to have those in your plant. In fact, most vendors offer the software for free. Like if you go to our website, you can actually download the device care software to talk to our staff for free because being able to pull envelope curves is so helpful and just communicate with
Sure.
your instruments.
Yeah.
But with those curves, I can tell you, do you have an interface layer? I can tell you if you have a rag layer in your separators. And we can start getting into the nitty gritty of, are you getting condensation on the face of your sensor? I can see the weld seams in a pipe if your radar is mounted over it. Yeah. So it's kind of funny. Like I'll find I-beams in people's tanks that they didn't even know existed. So, and they're like, oh, wow, we didn't even know that was there. So using those signals, and you can do that with a pulse radar too, but being able to see all of that is really cool and fascinating. I mean, at the end of the day, most people want to put their radar on top of their vessel and forget it exists until it dies in 10 years. Yeah, if you really want to get into the technology, I love it. I guess some of this would have actually answered the questions on this slide. So the FMCW technology allows for longer measuring ranges, right? The linear frequency sweep and large bandwidth because you're modulating between 4 gigahertz, right? Yep. It allows higher accuracy compared to process pulse radars. So we're talking millimeters difference, which in a lot of processes, plus or minus 1 millimeter versus plus or minus 2 to 3 millimeters isn't a big deal. But if you start talking like custody transfer or billing, like if you're billing on what you're pulling or adding to a tank, then it becomes very important. When you have that slightly higher dynamic range combined with the narrow beam, it's going to help you in more demanding applications. And the more narrow signal shape compared to other FMCW systems, because you can use FMCW at other frequencies as well, right? But using it at 80 gigahertz increases the range resolution without signal loss. Pulse radar is ideal for lower frequencies such as 6 or 20 gigahertz or 26 gigahertz. So you can use FMCW at a lower frequency, but because your lower frequencies don't have as much energy, using the pulse technology is actually better.
Okay.
It's more proven. You still get fast sampling and easy signal evaluation, and it fits ideally for 2-wire. It's also more robust and fast moving and boiling surfaces. So earlier, I kind of mentioned that 80 gigahertz, it's going to struggle more with fast boiling or fast moving surfaces compared to 26 gigahertz. Now, when we get into the algorithms of the device, there are some things we can do to mitigate those impacts. But in general, by using lower frequencies and using pulse, you can mitigate those effects without special algorithms or programming compared to 80 at FMCW. One of the big things I wanted to talk about too was level measurement outside of radar.
Okay.
We spend a lot of time discussing not only is 80 gigahertz the end all be all frequency, which as we've kind of seen, it's not, but is radar the end all be all at all, right? And when it comes to level measurement, I like to take a fit for purpose approach. So one of my specialties in addition to radar is actually our radiometric solutions. And that's for like the really heavy stuff. That's for, if you have something that's extremely abrasive, it's super hot, it's, you can't put anything in the tank, you're going to kill your radar because of either the process or you have multiple interfaces in a tank that will build up on a guided wave. Then you look at something like gamma, right?
Yeah.
And all of these level technologies have a time and a place. Capacitance is kind of the OG level measurement outside of pressure, right? We started as a capacitance company.
All right.
And if it's actually the fastest moving level technology. So if you have filler bowls, capacitance all the way. And so I just kind of wanted to take the moment to, remind people like, hey, there's so much cool stuff out there. Radar's great. I love radar. And I do actually really like 80 gigahertz. But we have to keep in mind, like, let's get something that's right for the process, right? And not focus as much on the thing with the new shiny bells and whistles.
Now, would Endress+Hauser have all of this?
Yeah,
All of
this
these
is all stuff
options?
that we provide. We
Okay.
sure do. So everything from microwave barriers, paddle switches, float switches. Again, capacitance was our OG level
Okay.
measurement.
Yeah.
That's where we started as a company.
Mhm.
I've worked on capacitance probes older than I am, and they're still going strong. And yeah, to find the manual, it was literally digging up a hand scanned in manual that was on somebody's
Yeah.
jump drive that they'd saved, but it still worked just fine. Ultrasonic, a lot of people are trying to move away from ultrasonic, and don't get me wrong, radar has taken the place of a lot of ultrasonic.
Mhm.
But if you have a concrete wet well and that thing's ever going to run dry, your radar signal is going to get lost. It gets absorbed in the concrete.
Mhm.
Whereas if you throw an ultrasonic device in there, it's going to measure strong every time. The pulse on the face of the sensor from an ultrasonic device helps clear condensation over wet wells too, so you don't interfere with your signal. So there's a time and place for all of this.
I want to ask about the radiometric. Does the tank wall, what the tank's made up of, does that affect the product you select? Because they have, plastic tanks, they have metal
hmm
tanks, they have stainless steel tanks. Do you have to choose the product based on the tank they're using?
For radiometric specifically, or just
Yeah.
for level in general?
Well,
So
for
radio,
radiometric,
yeah.
because you're sitting
So
outside of the tank looking through it, right?
yeah, so with radiometric, the only thing you're really going to size, so the context of radiometric is simple. You have a nuclear source on one side of your pipe or vessel. I say simple,
Mhm.
but we're dealing with nuclear. And then you have a detector on the other side. I know. I say that a lot, but I also deal with gamma a lot, so it
Mhm.
seems simple to me, right? And you emit radiation into the vessel, and then you measure the counts on the other side with a detector. So
Okay.
the only variables you're playing with are what type of source are you using and what size of source are you using. So the two radioactive materials we use are cesium and
Mhm.
cobalt.
Okay.
So cesium 137 and cobalt 60. And depending on how thick the vessel is,
Mhm.
or do you have heat jackets you're trying to get through,
Sure.
that's going to let us know which source we need to use and what size. So cobalt 60 has a much shorter half-life than cesium, so we
Okay.
prefer to use cesium. The half-life of cesium is 30 years, cobalt 60 is about 5.5. So you have to, every 5.5
Replace it.
years, depending, yep, you have to replace it. And
Yeah.
that's, working with the NRC, that's source disposal. So if you can use cesium, it's great. 30-year half-life, and in 30 years, we're going to have a much more sensitive detector, so you probably won't have to dispose of it anyway. I mean,
Oh,
that's,
yeah.
yeah, we're seeing that in the market right now. We have an extremely sensitive nuclear detector, and so we can mount it up to 30-year-old sources that are at their
Mhm.
half-life, but it's still big enough for the detector. Sometimes even more so. You have to put steel plates in between the detector and the source to kind of bring down the radiation.
Oh, okay. Now, is this something
It's
you
really
can't
cool.
stand next to as a person when you hear
Uh,
radiation, right? Is this
I
like an
mean,
X-ray?
so I'm going to say it depends. In general, we're working with source sizes that are so small, you're going to get more radiation on an airplane,
Okay,
right? Yeah, it typically.
typically, good.
I say typically, there's an exception to every rule, right?
Sure.
But in general, the process that you're putting this source on is going to be much scarier than the source you're putting on the process,
Good point.
right?
Yeah.
Yeah, it's a last resort measurement. As much as
Mhm.
I specialize in it, I do recognize people want to move away from radiometric where they can. It's costly, and people are scared when they see, the
Yeah.
radioactive symbol.
Yeah.
Even if yeah, I mean, radiation safety is all just time distance shielding, and I understand that, but it does still scare a lot of people.
Yeah. Yeah.
Um, and again, I get that. I think that before I started to learn, the safety side of it and how, I mean, we're exposed to radiation all of the time. I mean, I'm being
Sure.
exposed to radiation with my headset on my head right now.
Hmm.
Um, I'm less scared of it,
Yep.
but plants want to get away from it. It's a little costly, but
Yeah.
it is a tried and true measurement, and it is very safe.
Yeah. Especially if you can't put your sensor in your tank, I could see why that would be appealing. Um,
hmm
this is great. I love that you have this slide here. That this is slide 17 for the audio audience, but you're kind
hmm
of just showing really all the different ways of level measurement. outside of radar,
Hmm.
guided radar, ultrasonics, you even got float switches in there, paddle switches, So
Hmm.
yeah, that's a good summary of all the different, and these are all products that you guys make, like we said. So very cool.
Yeah. Yeah. No, we make all of this. And I would love to call attention to like measuring level with pressure. That's probably one of the oldest ways to measure level as well, and super, super common. So I feel like that guy gets overlooked a lot. And having pressure in my basket, it's also near and dear to my heart.
Yeah, yeah. I mean, what
Hmm.
what would you say would be the best use case for the pressure, measuring level by pressure
Oh
versus other
man,
means? Is it just inexpensive, or because
it's
it's non-contact, right?
suspended solids is a good one.
Okay.
Particularly foamy processes.
Mm-hmm.
When I think of dairies, especially, I think of
Okay.
hydrostatic level measurement. So when you get into a lot of milk tanks, one, you have to adhere to PMO, which is pasteurized milk ordinance,
Mm-hmm.
and two, you're going to have a lot of foam. And so having hydrostatic level measurement allows you to ignore the foam because it's not picking up on the density of the foam. And you still get an accurate level. They also adhere to pasteurized milk ordinance. You can get them electropolished. They're easily cleaned, right?
Mm-hmm. Mm-hmm.
Sometimes we're using pressure for level just because those are the ports that we have open on the vessel.
Ah,
You might not
okay.
have any ports on top left anymore. So we
Mm-hmm.
can use a differential pressure level measurement, especially in a pressurized tank, and get level that way. So if we're helping customers spec out a level measurement, what's in the tank's important, how hot or how cold are we getting? Obviously, if this is cryogenic, that's where the how cold comes in.
Sure, sure.
What ports do we even have available? Can we install something on the top? Or even if we can install it on top, are there other obstructions that are going to be in the way, like an I-beam?
Mm-hmm.
So you start getting into the nitty-gritty of how the install, the product, and the conditions. And that's why I personally really like a fit for purpose approach.
Now, let me ask you, like with the I-beam, you could, if it's not moving, right, you can
Mhm.
mask around it, I'm assuming?
It depends.
Okay.
Yep. So that's where the beam width comes into account.
Okay.
So if I have a 26 gigahertz radar with a wide beam width and the I-beam's on the edge of it, sure, you can map that out. We call it mapping. So
Mhm.
you can suppress that false echo. But if you have an 80 gigahertz radar and it's mounted right over it, you can't see past it at all because you can't see through the I-beam.
I want to ask you this too, and this may be way off the topic, but I'm thinking a lot of times the agitators in these tanks, they actually go pretty close to the wall, right, of the tank.
Hmm.
Not all of them, but sometimes they do. And I'm wondering, how do you, like, if it has a constant speed, I guess you could mask that out somehow. But I mean, are those well, how do you deal with that when there's an moving agitator that you really can't shoot around?
Sure. So we do what's called a map overlay.
Okay.
And if you can run the agitator with the vessel empty, you
Hmm.
can tell the instrument to map while the agitator's running. And then it can
Oh,
actually
okay.
learn that part of the process.
Okay.
And yep. So as the agitator's moving, it knows right where that agitator's going to be because it'll, even if the agitator blade's only going under it every 20 seconds versus every minute, like you're changing the
Hmm.
speed, it still knows what that signal is going to look like and to cancel it out.
Ah, okay.
Hmm.
That's awesome. Yeah.
Yeah, they're really smart instruments, especially now.
Well, actually, I don't know if I have any more questions. I really bombarded you, but I
No,
really
it's
appreciate you
okay.
coming on. Did you have anything else you wanted to cover today?
I think that's all. I mean, just kind of a wrap up, nothing against 80 gigahertz. I love it. We're pushing out really cool products with it. I just really wanted people to know that there's so many other cool things out there, especially if you have an application that seems really difficult.
Yeah, I think we all get into that. We all fall into that trap sometimes of saying, "Hey, this is the cool new thing. I'm going to use it for everything." And then that
Hmm.
application comes around. I mean, like you said, one out of five that it may
Yeah.
not work for. It may not even work at all. So it's
Mm,
good to
yeah.
know that. I think this was a great, and for me, this is just like food for the mind. So I really appreciate you coming
Hmm.
on. I hope the audience, you guys listening out there, you guys and gals listening out there, I hope you enjoyed this too. And I hope we can get Endress+Hauser back on in the future to talk more about this stuff because it's just so interesting. And again, I'm learning as you're talking, so it's not like it's something that I've
Yeah.
done 100 times in the last 34 years. This is a lot of stuff that I never really got into. So I love learning about it. So Ashley, thank you so much for coming on. I really appreciate it.
Yeah. Thanks for having me, Shawn.
Well, I hope you enjoyed that episode, and I want to thank Ashley from Endress+Hauser for coming on the show. and bringing us up to speed on 80 gigahertz radar. I learned so much during this episode. I hope you did too. And if you did, please consider giving us a like, a sub, and a share. That is the fuel that keeps this show on the air. Also, if you want to get in touch with me or just follow me, you can do so over at automation.locals.com. And you'll always find all of my training courses over at theautomationschool.com. With that, I want to wish you all an awesome week, and I want to encourage you, no matter what happens, stay courageous, stay fearless, and until next time, my friends, peace.